Hello, friends. We're continuing with our study of geometry, and this next lesson is not going to seem a lot like math, especially for people who are used to just kind of algebra, because we're going to be looking at logic. You're thinking, this is logic. Why are we studying logic? This is a geometry class. Well, the answer is that logic is really the basis of every subject. You want physics to be logical, you want math to be logical, you want philosophy to be logical. I've taken logic classes in both the math department and the philosophy department, and the basics of it is all the same, but then it's the application of it, how it plays out. In your math journey, you've used logic before, but you don't realize that you've used it. In geometry, we're going to be trying to prove ideas, to start with one idea, a couple of ideas, and then move on to another idea and know with 100% certainty that it's true. And so, in order to know that and to know how that works, we've got to understand logic, how logic works, and the processes. So, this is lesson one on logic. Lesson one is the way that we learn most things, the way most of our everyday kind of logical activities work. And this is what we call induction. Induction is when we find patterns. This is the way that science works. We come up with a hypothesis and we test the hypothesis. Okay. In math, we call it a conjecture. And so to help us learn about this, I have an example. All right. It's a game that I play. It's something I do with my students, and we'll see if you can figure it out. I'm basically going to give it away, but that's okay because we're learning about logic and how this works. Inductive reasoning, which basically means just finding patterns. So I start off with three dice, and I tell you that the name of the game is how many polar bears are there around the hole in the ice? It's the name of the game. And so the object is to look at the dice and to figure out somehow how many polar bears are there to answer the question. I'm telling you to start that with the dice the way they are now, the answer is um, four. There are four polar bears around the hole in the ice. Okay. So you've got to use that and you make a conjecture about how I got that. And you could say, well, so here's an example of a conjecture that you might come up with. Well, there are four, that's the smallest number here. And so the conjecture is that the smallest number is the number of polar bears around the hole in the ice. Okay. How do we test that? Well, the way that we test it is we do it again. So now I'm going to re-roll the dice. And based on the dice that we have here, based on our conjecture, which is that the number is just the smallest number on the dice that we rolled, the number would be one. Okay, so according to our conjecture, the number is one. But based on the rules of the game, the number of polar bears around the hole in the ice is actually eight. So what we've done here is we've given a counterexample. Right? If we have a conjecture, it's an idea that we're testing to see if there's a pattern. All we need is one counterexample to disprove the conjecture. That's it, only one. Uh, and that's happened many times in physics. Again, this is the way that science works. Physics, people have come up with an idea. There's a conjecture or a hypothesis that they have, which is really what we call it in science. And someone will do an experiment, or there'll be a couple of experiments that then disprove that hypothesis. And so they throw it away and they move on. But that is progress. That is making progress because now that's one thing you didn't know before, that idea doesn't work. That's assuming, of course, that all of the experiments were done correctly. It's also happened that there's an idea, people are like, oh, it's disproven because of these experiments. And it turns out the experiments were wrong or the data wasn't being analyzed correctly. So you got to be careful. It's a complex process. It's not quite so simple. So anyway, here, back to this conjecture. So we're down a conjecture. So we got to come up with something else, right? And rather than drag this out, I'll lead you through. I'll help you find a conjecture, and then you can continue to test it um, here, right? And so the whole lesson, by the way, is simply this idea of inductive reasoning is finding a pattern. A conjecture is a hypothesis. It's an idea about how the pattern works. And then a counterexample is an instance, a phenomenon, some example that disproves the conjecture. That's basically the whole lesson. So let's go back to the polar bears. This one, if I just simplify it to one here, there are four polar bears around the hole in the ice. Okay, how do I get the number four? Well, let's remember that the name of the game is how many polar bears are there around the hole in the ice? Well, if there are polar bears around the hole in the ice, where would the hole be? And what color are polar bears' noses? And so with that in mind, as we look at this, there are four polar bears around the hole in the ice. Here, there are two polar bears around the hole in the ice. This time, there are no polar bears around the hole in the ice. For this one, there are also no polar bears around the hole in the ice, because again, if there are going to be polar bears around the hole in the ice, where would the hole have to be? Here also, there are no polar bears around the hole in the ice. So this was the most recent instance we had, and I said there are 8 polar bears around the hole in the ice. And so you're looking at each of these and just counting how many polar bears, how many noses there are around the hole. And so in this case, there are 8. The first example we had was, I think it was like this. And I said that there are 4 polar bears around the hole in the ice. So you can see we thought it was just the smallest number, but now we can see why. And again, what you would do is you would just test this over and over and over again. One of the interesting things about inductive reasoning is that through inductive reasoning, we never actually prove anything. We don't prove that we know it with 100% certainty. The next thing that happens might then disprove our idea. This is what happened with Newton's theory of universal gravitation. It worked. It worked great for many years, but then at the end of the 1800s, there were observations of the planet Mercury that didn't line up. So there was a problem with Newton's theory of gravitation. And then it was modified by Einstein's theory of general relativity. And so we just keep testing over and over and over again. And in the case of science, even Einstein's theory of general relativity, they're continuing to test it, continuing to put it to the test and see, does it hold up? Are there any counterexamples? And a really good theory is one that has held up to many of them. So again, to summarize, inductive reasoning is finding a pattern. That's just what it means. The counterexample disproves a conjecture. A conjecture is just an idea about what the pattern is. So thanks for watching. Hope you enjoyed this introduction to logic, and don't forget to like and subscribe.